So my interest in the foundations of quantum mechanics is a natural byproduct of my interest in the foundations of physics, which arose from my interest in the nature of the world. My original undergraduate degree was a joint degree in physics and philosophy because I was drawn to foundational issues generally. The way one might be interested in mathematics, asking what numbers are, or what is the basic structure that allows mathematics to exist rather than doing very specific things. You can ask about the physical world at the most basic level. What kind of thing is it? What kind of structure does it have? And if you follow that line of inquiry, you obviously are led to quantum mechanics, and you find in your physics classes you don't get a clear answer to any basic questions of that kind. So you're in the curious situation that to understand the physics, you get led into foundations of physics, which then is done sometimes in a kind of philosophical setting, and sometimes in a more mathematical setting, and sometimes in a setting of physics departments, but is fairly distinct from what the physics you learn in your normal undergraduate program. Yeah, I don't think that that particular question is a terribly useful one. What we know is that there's a kind of recipe, a practical recipe that you learn for using a mathematical formalism to make predictions, and that formalism does a spectacularly good job of making predictions. But when you try and ask yourself the question we talked about before, what's that formalism telling me about the physical world, it's not at all clear. All I want is clearly formulated theories that have as a consequence of them that the normal techniques should work. Right? A clearly formulated physics that I can analyze and understand in terms of it why the normal quantum mechanical procedures for making predictions should be accurate. And there are different ways to do it. One thing we found out is that very different theories that tell you very different stories about the world can do that job equally well. And I don't think among those any of them is more or less like quantum mechanics, because all you can mean by a theory being like quantum mechanics is that it gives you at least approximately, and to the extent that we've been able to check, the quantum mechanical predictions. That's getting the quantum mechanical part of it right. And even theories that tell you very different stories about what's going on beyond that, you need to judge, if you're going to make a judgment at all, on different grounds. You might ask whether some are more simply or cleanly or elegantly formulated, or whether the mathematics hangs together in a more natural way, and so on. But those are no longer judgments about which one is more or less quantum mechanical. Well, it need not be at a fundamental level. I mean, randomness shows up experimentally because you do experiments repeatedly, having tried to prepare the systems as much alike as possible. And you find, nonetheless, no matter how carefully you try and prepare them exactly the same way, you get different outcomes. And those outcomes are, in a certain well-defined sense, randomly distributed, dots on a screen that show up sometimes here and sometimes there, or the Schrodinger cat kind of case where the cat would end up sometimes alive and sometimes dead. So that's just a fact about the world. And somehow a good physical theory has to explain that fact. There are two approaches to it. One is that there's a fundamental kind of randomness in the very dynamics of the world, that the world, how the world evolves in time, involves some indeterminism or some randomness, or the possibility allowed by the basic physics that it evolve one way rather than another. And the reason we're getting different outcomes in different times we run the experiment is that the world, as it were, without any further reason, has decided in one run to go this way and in another run to go that way. That's one way to get random results. The other is to say, no, there's always something that predetermines the outcome of an experiment. We can't control that, we can't prepare that, and all we're doing is sampling through the different possible ways it could have been precisely set up at the beginning, and that sampling is a kind of random sample, so you get randomness that way. These are two very different pictures of the source of the randomness. Again, at the end of the day, what we want is to get the data right, and each of them is a way to get the data right. So the implications of the observed randomness really depend upon the theoretical construct that you're using to account for it. So that's easy. The fact that we can reliably see violations of Bell's inequality for experiments that are done very, very far away, and as far as we can tell, according to the theory, as far away as we like, means that there has to be some real physical connection between systems, even if they're very distant from one another, which is just something you wouldn't expect at all on the basis of classical physics and what we call non-locality. And that is something that's unavoidable. It's what Bell showed is that any theory, no matter how it's constructed, as long as it was local in a certain way that the physics just depended, the physics in a region would depend entirely on what's going on in the nearby regions. No such theory, no matter how you put it together, will violate these inequalities. The fact that they are violated then means that there's something non-local going on. How to understand that non-locality, how to represent it in the physics is an interesting question, and again, you can't determine that simply from the violations, but it does tell you that physics is going to have to look quite different with respect to the locality conditions than all of classical physics. So this is one result from quantum physics that will have to remain no matter what kind of theoretical changes happen in the future, because it's simply the outcomes of laboratory experiments that tell us that there's some non-locality in the world. So philosophy doesn't really bring specific content that's going to help physicists, not surprisingly. What a philosophical training or a philosophical sensibility brings is a sensitivity to precision and clarity in certain questions. Particularly, philosophers have thought a lot about the relation between representations and what they represent, and mathematical physics tends to use very abstract mathematical objects to represent the physical world, and it's not at all clear how to understand them as representations of the world. It's not at all clear, even though you know how to use them, manipulate them, use them to make predictions, how to understand them as telling me about the world in itself. So I think the great physicists who dealt with foundational questions in the 20th century, first and foremost Einstein, and then in the second half Bell, would have made, and in some sense did make, great philosophers, just in the sense of their sensitivity to clarity and precision in certain conceptual questions. And at least some kind of training in philosophy will heighten your understanding of the problems that come up if you're not being perfectly precise in the words that you're using, and so can be of help to anyone who's dealing with very difficult and abstract matters like this. So I guess there are problems in the foundations, and then there are problems that relate to what would be recognized as the basic problems in physics. The most pressing problems in foundations is simply to get as many clear, precisely defined physical theories that seem to return the predictions of quantum mechanics as we can, and usually that means beginning with just getting a kind of theories in very simple, non-relativistic domains, and then trying to extend them to relativistic domains. And there are lots of technical problems to work on there. And then there are problems that physics itself hasn't solved. For example, how to bring in gravity into quantum mechanics, or to marry together the general theory of relativity and quantum mechanics. This is the sort of problem that any physicist would recognize as an ongoing problem. If you're doing foundations of physics, of course, at the end of the day, what you want to do is understand the foundations of the correct physics for the entire world. We don't have that yet. And as progress is made in that direction, there will always be more work to be done in trying to really clarify the foundations of the sorts of theories that physicists come up with. So those problems of how to extend and unify physics generally come down to foundations because they're just problems for physics, and the foundational problems are how to understand any of these theories in completely clear and precise ways.